Alright, so we're going to be talking about gradient descent today. And so I'm just going to briefly give an overview of gradient descent, and then we're going to switch videos and we'll go to the desktop here and take a look at some examples. Okay, so what is gradient descent? Um, it's a method for finding, actually well, we'll be using it for finding the local minima, but it can also be used for finding local maxima. And so altogether then you could use it for local extrema. And the whole idea of the algorithm is based on the following theorem that we've seen in Calc 3. The gradient of a function at a given point will point in the direction of the fastest increase. I didn't realize I had point twice there. So if you're sitting at a given spot in the domain, the gradient will point in the direction of fastest increase. And so if you want the function to increase the fastest, you will move in the direction of the gradient. If you want to move in the direction of fastest decrease, what do? That's the negative gradient. Okay, so in our algorithm, we'll just start at a point, we'll compute the gradient, and then we'll move in the direction of negative gradient. That's the entire algorithm. Let's take a look at some of those pieces a little bit more. Typically, the function that we're going to be looking at is some kind of error function or loss function, and so that's why we're going to be minimizing it. We're going to be trying to find parameters for the function, very much like least squares, linear least squares. That's not what I want to say. Linear regression is what I want to say. So you're finding a line of best fit, and so you're trying to find a slope and an intercept that minimizes an error function. And so you could use gradient descent for that. And in fact, we do in an example coming up. Okay, so gradient descent as an algorithm then, you just, given y equals f of x, notice, by the way, that this is a multi-dimensional domain, but the range is one-dimensional. You have to have real values for this. By the way, you can optimize in the complex plane, but for us, we'll stay in the reals. Okay, and so then you just iterate this formula over and over again. So again, once you have x0, you plug it in to the gradient, you compute that. Alpha is called your step size. That's the you can think of it as how far in the direction of the gradient you want to go. And so we just take xt plus 1 to be our base point minus the alpha times the gradient. Good, it's very simple. So let's take a look and see how this works. If we just have f of x squared, for example, you could use gradient descent to find the 0. So you would just start at a point and you would compute the derivative, and in this case the derivative is a large positive number, and so that means that you would go to the left, right? Because you go in the direction of minus the gradient, and so minus in the xy plane, or in the x number line, we only go one of two directions, right? We can only increase or decrease in our domain. So in this case, if the gradient is positive, or the derivative is positive, we go left. And so we would move left for however much of our step size is. And then, at this point, we might be at this point, for example, and then we would still move left. And then you might actually overshoot the minimum, which is possible. And so if you do, what happens? Like if you're at this point in your domain, you see that the derivative is a negative number, and so that means you want to go to the right. Yeah, so you would increase your x value in that case, and then pretty soon you would end up kind of, hopefully you'd end up at the origin. Good. Another way to look at this is that you can think of gradient descent as a ball rolling down a valley, on a valley. And so in this case you can kind of see several initial positions, and the arrow shows you the initial direction that they would travel, right? So the direction is taking you downhill, and so hopefully you end up in a valley, So it also shows that what happens often in these problems is that you get trapped in some local minimum, and that's just a consequence of our algorithm. That's not a problem really. That's just what gradient descent does, right? So hopefully what happens if you start at enough positions in the domain, right, as initial starting points, hopefully you can find the location of the global minimum in the region of interest. Okay, so that can be kind of tricky. So practitioners usually restart gradient descent several times to see what the value of the minimum is, or what their best minimum is so far. Okay, so that's a good practice in general. Remember what we did in k-means clustering too. We had several restarts just to see what the algorithm would converge to. All right, so as a numerical example, here's a function, and we're sitting at a 0.11, and we would like to reduce the value of the function. So what is the value of the function right now? 3 minus 4 is minus 1, plus 1 is 0, minus 3 plus 2 is minus 1. So the value of the function right now is minus 1. And we're going to see if we can decrease the value of that. So at the 0.11, we compute the value of the gradient, and so we need our partial derivatives to do that. So f sub x is 6x minus 4y minus 3, and our other partial derivative, minus 4x plus 2y. The 2y is coming from here. I was going to say that's not right. Plus 2, there's the 2. Okay, and so when we plug in the 0.11, what do we get? 6 minus 4 is 2, minus 3 is negative 1 for f sub x, minus 4 plus 4 is 0 for f sub y. Okay, so again, that's our gradient now is minus 1 comma 0. And so our gradient is minus 1 comma 0. That's the direction of increase, so we want to go in the direction of negative of that, right? So we would go in the direction of 1, 0, meaning we move to the right in our domain from the 0.11. Okay, and so let's compute our next point then. To compute our next point, we want to go in the direction of the gradient, so x0 minus alpha times the gradient of f of x0. Let's compute that expression. So that's our x0 is 1, 1 minus alpha times minus 1, 0. And notice that you can simplify that, and these become linear expressions in alpha. And so what we're going to do next is plug this back into the function for x and y, and that would mean that f is a function of only one variable in that case. F would be a function of alpha. And so what happens when we do that? Because I should tell you what the problem is here. The problem is we don't know how big to step in the direction of the gradient. Sometimes we could just take the step size to be a small positive number and just keep it that way through all the iterations. But sometimes it might be useful to see how far you can step before the function starts to increase again, right? So if we move in the direction of the gradient, we should be decreasing, but at some point we're going to be increasing again, right? So we'll start to decrease, and then we'll start to increase. And this all depends on a single parameter. So this is when you plug 1 plus alpha in for x and 1 in for y. This is now an expression only in alpha, and so we can find the minimum of that real easy. All right. So again, if I plug in 1 plus alpha for x and 1 for y, I get this expression, which is just a parabola. And how do you find the minimum of this parabola? It's just the value of the vertex. So you could simplify this out, or you could take the derivative, set it equal to 0, and that's what I did here. So once you take the derivative, set it equal to 0, we get alpha is approximately 0.16. And so that means that if you move like 0.17 in the direction of the gradient, the value of the function is going to start increasing again. So this is the best we can do by going 0.16 units in the direction of the gradient. Okay, so then we go ahead and plug that in to find our x1, and so now x1 is equal to 1.16 comma 1, and our new value of f is slightly smaller, not very much. So we must be fairly close to the minimum anyway. And so now we just repeat over and over and over again. So again, what do? You're at a point, compute the value of the gradient, figure out a step size if you want to, and once the step size is found, then you just compute this this expression to find your next value. And you just keep on rolling that over and over and over again. What are some possible stopping criteria? Well, we could hit some kind of maximum number of iterations. That's possible. Anything else? What are we looking for? We're looking for where the gradient is equal to 0, right? That's the whole point of this exercise. And so what we could do then is to see if the absolute value, or the size, or the length of the gradient at our current point is very, very small, which means it's going to be less than some tolerance level, some epsilon. And so that's another good way to stop early, because you don't want your gradient to get too close to 0, I guess. And then another way to do it, right, is to see if your x values are actually even changing very much. You may not be even moving in the x coordinate, or in the x domain very much, right? You may just be oscillating back and forth by some little epsilon. And so in that case, you would want to stop. Of course, if you have a maximum number of iterations, that's guaranteed to make sure that you don't have issues with that. Good. So what we did is do a line search, and sometimes the step size is fixed. Now we're going to stop here and go to a website. This is really a nice website because it has some interactive graphs in it. And so we'll continue from there.